live. Some of us are wearing face masks, and I want to say you still look fantastic in Opto Sigma laser components. Why don't we get the ball rolling? Welcome to the Epic Online Technology Meeting on 3D and Advanced Metal Manufacturing. Okay, start the engines. Let me take you back to the year 1850, the start of the Industrial Revolution. Most people think it means machines replacing humans, but in fact, it was all about manipulating metal in an automated process. Fast forward to 2001, the telecom bubble explodes, and at the same time, companies developing photonics see a huge opportunity in laser-based manufacturing. 10 years later, 2011, Industry 4.0 was first introduced. Year 2020, Monday, October 19, 3 p.m. Central European Time, we discuss advanced and additive manufacturing of metal. Steel remains the driver of the macro manufacturing world. Processing steel effectively is a secret to success, and photonics is that key to success. With lasers, we can weld, cut, drill, 3D print steel. With optics, we project the right beam shape. With infrared cameras, we monitor in real time. As a result, we satisfy the precise needs of automotive, avionics, naval, civil engineering, as well as those making medical implants. My VIP guest list includes ArcelorMittal, Airbus, Stryker, GE, Trump, Siemens, and BMW. So plenty to talk about on Monday, October 19th at 3 p.m. in the Epic Online Technology Meeting on Advanced and Additive Metal Manufacturing. We'll have prominent users and the complete photonics supply chain in our Zoom room. Don't miss this opportunity to ask questions and enlarge your network, because in this business, disruption is the only constant. Thank you very much for this. It's been a lot of hard work behind the lines. Francesca has been putting together all the supply chain of companies here to do business in 3D printing and advanced manufacturing. For me, I have to say that I keep being amazed by the success of these online meetings, amazed by the connections that the companies are making, amazed by the fact that, I don't know if you're aware of this, many of you got it in the newsletter, we are now the biggest photonic association on planet Earth with 650 members. And this is incredible, the support that we keep getting from the industry. On our online meetings, we also keep getting a lot of support from all of you. Many people are watching in YouTube. Many people are asking us to contact companies afterwards. This has been a great success. Please have a look at the upcoming events from here to Christmas and notice that we have lots of interesting meetings. For example, on the meeting today, compare it with the technology that we are actually addressing on 14th of December, industrial lasers for manufacturing on naval and aeronautics. This is going to be a key event also to connect with the users of these particular market segments. I also want to say that I am only here talking on behalf of an amazing thing. I'm so happy to be part of this. We organize events, we provide access to the network. We also have access to investors. So if you are looking to raise capital and you're a member of Epic, please contact us because we have a large network of investors. We also have the largest website to find a job in photonics, www.jobsinphotonics.com, largest website in the world to find a job in photonics. And we also provide a long list of market reports for free to all our members. If you have any question about market data or you have to do contact our technical team, we not only buy these market reports and give it to you for free, we also study them thoroughly. So if you want to know anything about this, please always contact us. But today is a 3D printing of metal day. I would like to start, of course, by thanking our sponsors. Without you, this meeting wouldn't be possible. Duma Optronics, all the way from the beautiful country of Israel. This is a company that helps any company with making instruments for manufacturing, from high-end manufacturing to mass production. So you are looking for high-power laser beam profiling, you're looking for beam analysis, you're looking for optical beam positioning, alignment of measurement systems, electronic autocollimators, you have to contact my friends at Duma Optronics. They are a fantastic business partner. And also DMC. DMC makes this software that controls the 3D printing machines. It handles all the steps of the process from CAD import to cooling down after the print. It's a key company for the automation of manufacturing, and we're extremely happy of having them at Epic. But also we're extremely happy of having Dr. Francesca Moglia at Epic as our laser expert. Francesca, ¿qué cosa mangiamo today?
Thank you, Jose, for the nice introduction. So here is the view, let's say the boring view of the agenda today. Of course, we love our speakers, but we don't like to have them like this, like one after the other one. It's much better when they are in small groups, the groups that covers all the supply chain of this topic. And so it's really nice to see how for advanced and additive metal manufacturing, you can have the end user. So it's really happy to have here at least 3-4 sectors of applications of metal in metal of additive and advanced manufacturing, but also there is the option to get it as a service. So in this technology, it is not only need to buy the machines, but also to have a service. So thank you for joining this. And one of these services is actually what is given by our EU funding initiative PULSATE. So not only in additive manufacturing, but in any laser-based technology. Then we have those who really build the machines. So thank you for being here as well. Then there is the future of the technology. So I really like to have the R&D also presented in this and represented in this room usually. And then we start with the real supply chain. So behind the scenes, there are of course a lot of laser manufacturers and system integrators that are interested in this topic. So welcome to you as well. And then all the other things that are also together with the lasers important. So there's system engineering, packaging and testing solutions that we heard already as sponsors as well. All the optics and optomechanical parts that are really, of course, important. And of course, the distributors that are really interested also in this topic. And then, of course, you don't have a machine without a monitoring system. So it's really nice that also monitoring machine and monitoring experts are here today, like our other very interesting European funding initiatives, multiple. So, but now I guess it's time to start. So we really get into the dinner or well brunch, no, late lunch of today. Back to Jose.
Eating is nice, but when you have a person who has been actually preparing the food and serving it like Francesca over the last 2 months, I would like to say congratulations on behalf of all EPIC, because you are really positioning EPIC in the laser business like nobody else has done before. It is great to have this fantastic supply chain week after week after week. Thank you, Francesca. I also would like to say that for the companies who are thinking, oh my God, my logo should be there, this slide only represents the companies who registered for this meeting, and also for these few companies who actually registered in the last 40 minutes. And I'm looking at Benjamin from Infineon. We apologize, we didn't have time to update the slide in the last minute, but we are so happy of having Infineon and all of you who are registered also last minute for this meeting. And also we have a lot of audience in YouTube. So I'm going to say hello now to the YouTubers in the world. Hello, YouTubers. If you want to follow the meeting online, please stay in the YouTube channel. If you have questions, put them in the chat, but most important, if you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asoc.com, jose.pozo@epic-asoc.com, and I will make such introduction. This is all about connecting people. Also for the people in the chat, in the Zoom room today, all of you. We have an internal chat service, so use it to communicate during the presentations. And after the meeting, we have dedicated one-to-one meeting minutes that we're going to use for connecting each other. So you want to meet in private any of the other participants, all you have to do is tell our marketing manager, Suzette Germer, or PR manager, Suzette Germer, who is also in the Zoom room. Francesca, do you think it's time to get it all started? I'm going to leave it to you because you're such a rock star, such a hero. I'm going to leave it to you to introduce the opening speaker. Who do we start with today?
So today we start with actually the speaker from automotive. So we have Audi in the room, if I'm not wrong. I didn't see him yet personally, but he should be there.
Yes, I'm here. Yes, this is Martin Bock speaking. Yeah. Hi, nice to meet you.
Great, Martin. Thank you for joining us. So if you agree, I guess it's better if you explain yourself and introduce yourself and your technology at Audi at best. So the floor is yours. And if
yes, thank you very much. So we have a tight schedule, and also I will present only some small, very small issues about additive manufacturing and our viewpoint on these amazing technology. Of course, you see an e-foil.
Can you go, Martin, please, in presentation mode?
Yes, yeah. Like that one?
There you go. Perfect. Thank you.
So that would be a big wallpaper in the next 5 or 10 years, I think. You can drive with this e-tron e-foil over the sea. This is the Garda Sea. So we tested this board on the Garda Sea, And we printed this amazing board within 100 days of development time. So it's right now a prototype status, but it's publicated via Twitter, and so we can talk a little bit about it. So, so lightweight, aerodynamic, efficient, yes, of course, it's emotional, and it's a kind of outthinking of the box. Because what did you thought? Audi, okay, we are talking about automotive, autos, large ones, small ones, and so on. But this is maybe a little bit fantastic, and also thinking out of the box. Why we are here in Ingolstadt based, and we also think about fun, of course, and fun gear. So this e-tron eFoil was developed within 100 days. So very tight schedule. Therefore, we need additive manufacturing technologies. The jet turbine is only possible in AM technologies. So means I have to search about parts, defining parts who are only able to manufacture in AM, not in die casting, not in joining technologies or so on. So that's why AM stands for us also. So we have a small center, so only 3 machines, because we say we want to develop the technology. We want also to see what's happened with the machines, with the automated process, and therefore we have a small machine park with outstanding technologies, of course. And yes, it's quite all right for us from the capacity. So we understand the materials behavior, the surfaces produced, and if we need more parts, yes, we are going outside with the parts and produce these by distributors and also developers. So what's important? 4 engineers, 3 applicators, very small team, yes, really engaged, and we want to industrialize these technology. Also, we have only 3 materials, so all other materials will be also placed on the market. So if we need a part from titanium or so on, we need suppliers. Yeah. Because it doesn't make any sense to shift materials on machines, yes, every day or every 2 days. It doesn't make any sense, yes. You have to understand the material behavior in the laser melting process to improve the process. And all machines we have on the shop floor are improved by us. So means also we developed our own printing parameters for the last 5 years. We enhanced the production capacity, of course, of these machines. But of course, to be honest, we are in a prototype status. Therefore, we need this technology, not for manufacturing parts in a large scale, 1,000, 2,000 parts or so on, large parts for cars, interior and exterior. No, therefore, other machining technologies stands for. So it's right now prototyping perspective. So the material process, the powder bed process, everybody would know, I think, how to work. Otherwise, you can check this on the internet, and also you can request me after this meeting directly if you have any more information. I don't want to bother you with old informations or standard informations, you know. So, but what is important to understand, you have the melting process in the machine on the side, that's the central picture, but also you have to think about the complete process chain. Here you can see a tool insert manufactured in AM with a weight of approximately 55 kilograms. And a duration time, manufacturing time on the machine of at least 15 days. And then you have to think about the process of depowdering, the heat treatment process. Material properties are very important, and you can define these material properties you need during the heat treatment process, and also milling and eroding processes, and then the finishing process. So that's very important. And that's my main message. If you want to invest in these technology, think about the process chain, think about your knowledge along this chain, and then you have to prepare these process chain you have established on the market, or you have to extend this in your company. These are our 3 machines, very clean room, of course, but you see also these machines are not connected with each other. Also, one of the big steps and problems, getting more parts from AM. So these machines stands alone means they need also manual handwork, a lot of manual handwork to start machining processes, to also to watch about the manufacturing processes, means parts are expensive than from a serial tool or anything else. But why we need this? Yes, I imagined and talked about in the future. So no tooling is needed, of course, but you have very rough surfaces. If you take a look around here in detail, so surfaces are not clean, are not glossy enough for interior parts. So these parts will be used only in prototyping status. But we can shrink the delivery time for such parts from 12 to 1 week. That's the main advantage of the process, nothing more. So prospect of the technology, main drivers from the automotive is cost per part, yes, or fast services. If you have any problems in the daily business, I would say, sometimes you can solve these problems very fast with AM technologies, of course. Then the cost per part doesn't matter, but you have to see what's happened during these process. Prototypes are quite all right for motorsport, pre-series centered design studies, exposition or show cars, maybe also sometimes spare parts, yes, for the Audi tradition, also for Porsche manufactured parts, spare parts. And yes, equipment is also a big topic. As I mentioned, we are manufacturing tools for hot forming, tool inserts, not the complete tool, die casting mold inserts, also robot gripper, yes, of course. But we see a red light or a yellow light on so far serious parts. Yes, there were discussions in the last years about lightweight potential, bionic structures, but the problem of these parts is the higher cost per part. So no end customer will pay more for bionic structures or a little bit lightweight designed parts. There is no possibility, of course. So this is a very, very short introduction. So we can talk about each capital here, each column over 1 hour, of course, yes. But my goal was to finish this presentation within 5 or 6 minutes. And I'm nearly in the time goal, I think, I hope. And so if you have any questions right now, please write it or please comment us, of course. And so that's for me all to say.
Thanks a lot, Martin. Thanks a lot for the nice introduction to the topic. And also thank you for already exciting all the audience. So I have all my colleagues that are talking about foiling now. So, so it's good that, that you picked already, you studied your talk like this. So let's say, what I would say, as you saw, you put already this like traffic lights. So, and we know that the green traffic lights are those that we don't care about because it means there is all fixed already. So we wanted to concentrate a bit on the yellow and the yellow-red one. So it's exactly about, for example, finishing or serial production for 3D printing. So now I don't see questions, but of course, please tell me if I'm wrong, because otherwise I will pick some of the manufacturers that have to answer about the short future of prototyping, all serial production also for automotive for this improvement. So should I pick you guys or someone wants to wants to talk about it? Maybe Harry, switch on the camera, maybe he wants to say something. Harry from Additive Industry, you're muted.
Yeah, okay.
Now.
Hi. Hello, everybody. I'm Harry Kleijnen, Additive Industries, Senior Key Account Manager. What I hear from Martin is something which is enormous. And actually, in my presentation, I also will ask. I'm going one level deeper, and I will ask the Photonics community. I will share them a little bit about our challenges. An AM printer is mainly determined by the optic chain. That's and of course there's a lot of gas flow, but optics is the key component. Stability, reproducibility, predictability, that are the key factors today to drive serial production. And the technology in itself is quite young. We see absolutely progress in that direction, but that there's still a big opportunity to improve. That's something I fully agree with. Then integrated process chains. Yeah, that's something I also can talk an hour or more, or a day or more about that.
No, but then it's good that we are all on the same page. So it's good also that I guess all the community here is happy because if the Photonics can help you, of course, also in this, and we are pretty sure we can, it's of course good news. So it's very, very good news that we can, of course, help you like this. And then the other, if I remember correctly, Martin, the other like orange-red traffic light is also that you have to make a bit of post-processing, right?
Yes, of course. So post-processing is the main cost driver. So this is the unsoluted problem, I think, in this community, of course. There are some solutions. Also, we had some research on etching technologies driven by ourselves because we are lazy guys. Yes, of course. But we need more personal power, more knowledge, also more networking with each other to figure out what could be happen. So it's mainly also a task for universities. So it's not. I think it's not done within the next 2 months or 3 months. It would be soluted maybe in 1 or 2 years or 3 years, something like that, and also co-conducted by the European Union or something else. I'm not sure, yes, but yes, Francesca, you are on the right way, of course.
Martin, thank you very much. Yeah, Martin, thank you very much for being, first of all, for AUDI being member of EPIC. It is great to have you in the community, always looking for collaborations, looking for partnerships. That's why AUDI joined EPIC, to find connections with companies. It is your first ever EPIC meeting, the first of many, and people get the EPIC question. And the EPIC question is something very specific. Is what can you do for the others, and what can the others do for you?
Yes, so that's interesting. So also on the laser side, it would be interesting, what are the developments for the future? And also we can test, and we are able, having testing facilities for new solutions, bringing down the cost of additive manufacturing. This could be possible. So I think it's more a network, and also finding new ideas within the network, and also we can share our knowledge as automotive guys. Yes, it's a tough word because we are cost-driven, but yes, that's the truth.
So any EPIC member, I'm calling all of you, 600 of you, any EPIC member that is interested, that has some solutions for tools for hot forming, die casting molds, integration of function, or accurate robot grippers, you have to contact my friend Martin Bock. Martin,
Yeah.
the 3D printing center of AUDI was set in 2016, so it's 4 years now. It's all well established. You are doing prototyping for automotive. I would like you to think about the future. What is your preferred future? You had this meeting again in 2025 with Francesca doing that fantastic job again. What kind of things would you think you would be telling
A
us?
fully integrated system from the first programming of the part with bionic structures, automated applied on the part due to a complete manufactured part. So, and finished part. This could be happening in a production cell, fully integrated. And also we have nothing to do with powder, with the laser or laser parameters. So it will be done everything automatically. And the knowledge comes from the cloud.
That's the dream. That's fantastic. We have a question from AMPC Solutions. Arno, what's on your mind? Arno Gransma.
Yes, I had to unmute because otherwise maybe music is, or the sound is rehearsing. So what do you think about, besides with lasers, of course, the development of 3D print forms with polymers and metal powder in it, where you go via debinding and sintering to metal products?
This could be interesting, of course, to have these integrated solutions, but polymers and metal solutions will be divided. So there are two different streams, I think, to come to the part in the end of the day, but they can stand together in a room or in larger rooms, of course. Print farms, we have seen such ideas also developed in new projects, yes, but they should be faster. The process should be faster because the machines are more or less slow. So we develop parameters with 80 micron. We are very fast in the last years, but having 10 slow machines are not the solutions for 2 fast machines.
No.
So this is maybe such what I think. So so thinking in integrated process chains, of course, print farms. We haven't any print farm because we say we have these 3 machines. But I know there are print farms in the medical sector. Yes, of course, they have 60 or 70 machines installed, but nothing for us. So of course.
Okay.
Okay.
Thank you.
Okay, thanks a lot. Yep. And then, so because before, I mean, later on we will have SINTEF talking. So from the R&D part, we will have for sure a very interesting talk. But maybe we have also a quick hint from Celine from CA. Maybe she's a representative of the R&D Institute. So would you like Celine to comment on this? There is something in the future coming that maybe will help Martin for automotive and 3D printing there?
So yes, that makes me think about, so there's these 2 projects I think about. European project, there's one which is called the DEMOFAC, which work typically, it's not only about additive manufacturing, it's also more about production in general, to make production more flexible and to allow company to produce parts with more flexibility and with the ability to adjust the production line. So, and there's a part of this project which also deals with additive manufacturing. And something else I think about when you mentioned the network, basically, is the PULSATE project, because we aim to build a whole European network, which objective is to address this kind of issues and to help companies to find solution to those issues.
So the European Commission and the European companies and institutions are all there to help you, Martin. So I guess it's all set to improve the 3D printing also for all the possible sector of applications. So we just have to wait a bit, but they are coming. And then, Jose, we have a question from YouTube, right?
It's more a comment than a question, Martin, but I think it's interesting. Yuval Ophir, who is a very good friend of EPIC, he used to be the R&D leader of Elbit Systems. He's contacting us and telling us after the presentation from AUDI, he thinks that if you can 3D print the molds and then cast the parts, there could be an interesting advantage. The 3D printing of molds is something that AUDI is addressing, and is that something that you perhaps see some room for cooperation?
Yes, so especially we print tool inserts for hot forming, die casting, and plastic injection molding. So also what is right now set up is a molding system for the injection molding. So, and we printed this tool system directly by AM.
Thank you very much, Martin. I'm going to say hello to the YouTubers because they are contacting me, Jan-Hendrik Peters, Bruno Edgar, Ophelio, Novan Appleton, Yuval Ophir. If you have more questions, thank you very much for following the meeting. Back to Il Female Capo today. Francesca, the ball is in your hands.
Thank you, Jose. So I guess now we had a bit of introduction already talking with Martin. Of course, Martin, don't leave. Stay tuned that we will for sure discuss further, probably with further discussions and topics from the upcoming speakers. And one of them, we heard him already at the beginning, but now it's time to give him the floor. So Harry from Additive Industries, the floor is yours.
Yeah. Okay, you should hear me now?
Yes,
okay?
we do,
Yeah, okay.
we do.
So, okay, thank you for giving the floor. I'm going to share my first, put it in presentation mode and then see how I can get my screen shared.
So there's a green button below. You click on the, and then
click this.
Use the right screen.
Yeah. And say share. Just a little bit different from okay, and let me see what happens now. I'm going to presentation mode, which is
and it's the wrong screen as the usual.
Yeah, that's exactly what happens then always. Stop share, and I'm going to try to do a second attempt because this is not the first time this happened. Sorry for the small delay.
No problem.
It should be.
You can also otherwise switch once you are already in presentation mode, but if you want to do it again, you can.
Yeah. So you will see now at least there is a one.
It's not coming yet.
Not yet, but one moment. Now, once again, now it's either I have to get out of presentation mode.
Okay.
Or it is. Oh yeah, I have to bring you to the other screen. Sorry for this. So, because I'm a Teams user, which is
yeah, we have many of you.
yeah. Okay, and now it is not.
Let me see. Let me see. It's coming. Yes, there you go.
Stop. Okay, thank you. Okay, well. Yeah, thank you all for your for attending the presentation. And yeah, today I prepared a few slides to guide you through additive manufacturing as a machine vendor and give you a bit of history of our company, what we offer that's very compressed, and then some examples and a number of questions or challenges we face as a machine manufacturer and designer. I'm going to start my pointer option, laser option. So in one slide, on the left, you will see where we are coming from. Additive Industries, young company. We started in 2012. We are located in the south of Netherlands in a very high-tech oriented region. A number of technologies which actually are also usable into an AM machine. We have been growing all over the world. We are represented in Asia, of course, headquarters in the Netherlands and Eindhoven. We have P&AD centers, process application centers in UK, in the US, in the West Coast, service centers all over the world. Our goal is to bring this technology to really to industrial level, and for that we developed a system we call the Metal Fab 1, which actually incorporates a number of integrations and automation steps, which classical machines were done manually. But it's the beginning, it's not the end. That's also what I would like to emphasize on. But just some highlights. It's a machine which has 420 by 420 millimeter platform, 400 millimeter high. You can bring in up to 500 watt lasers, and where the automation already starts is with the automatic powder removal and powder reconditioning, having the capability to have more materials if you have more build chambers, and you have automatic job changes. The process in itself is here, it's the powder bed laser fusion. As Martin also mentioned, you already can have a day of talking about this process. But here it shows a little bit what this does on your part. You see these small lines, that's actually the different laser lines, but also shows you the very small details you already can achieve with this technology, which could be of benefit of making parts for photonics applications. So the machine in itself, it's automated in the largest phase, but our customers are allowed to start small with just a simple system and add automation, and then have fully integration with automated job stores, job storage, heat treatments, powder removal, part removal, and so on. So this for the machine in itself. And now going back to the application. So what kind of questions do we get from our customers? All our customers have different questions in a way that sometimes they embrace this new technology for the design freedom or the customization which you have, for example, in the medical field, like at hip cup here, which you can make patient specific. Or you go to performance drivers like temperature regulation. This is a crosscut of an electrical motor housing, and it gives you an increase in performance. We have customers who love the fast design iterations possible with this technology, like in Formula One, but also in certain areas in oil and gas and energy field. Like here in hydraulic blocks here on the right, once again, fast design iteration, but also on-demand manufacturing, especially in the spare parts business, in industries which incorporate have to maintain systems for a long time. They want to print on demand. They don't want to have all the parts on stocks because that is expensive, but also obsolescence risks. And some other examples here about the performance of such a part. This is a part printed out of titanium. It's actually a wheel suspension. It has fully integrated hydraulics. It also connects this electrical motor housing I showed you as one part. It has integrated hydraulics. You see a small hydraulic channel that's fed through that housing. And this was an assembly of multiple parts now printed out of titanium, lightweight, for in this case a university racing competition in electrical vehicles. But this is a concept. It's also made by generative design. You can see it by the special, let's say, more nature-like forms. So it's lightweight, full performance, function integration, and so on. Another nice example which we recently shared was we developed there's a Dutch project where we developed a wafer stage which is used into a wafer, let's say a chip machine from ASML in our region. And the goal of this stage is to make it as fast as possible, because you need to bring and do that at sub-nanometer technology. And by having, we could say, generative design, which also incorporates the constraints of additive manufacturing, we were able to print these parts just as a one piece, no support structure. You only had to cut them off. And then finally, they were milled because we needed to put some parts in that, some blocks. And the part itself is then floating on a magnetic stage, which very accurately positions that part on which is a silicon wafer, on which are the patterns projected to make the microchips. So here it was actually the design algorithm allowed us to give the part a better performance. With incorporating the constraints of AM, we could print it as one piece. And finally, the performance of the part was substantially improved, so we could run 20% faster with positioning compared to the actual design or the existing designs, driving costs down in microchip production. And finally, it's more what drives now our business case and actually also our end user, and that's something I would like to come on. So the optics in an AM machine are the most expensive point. Lasers are expensive. The optics, the beam shaping, the mirrors, the galvanic mirrors, any optic window they are really driving the costs. And typical components already mentioned, the laser, but also the protective windows where we have the IR protection in front of the build chamber when you look into that glass, into that build chamber. So in our system, we use a principle we call dynamic focusing that allows you to project with the lasers on the full field. But you can imagine if you do this in a fast way, these are, well, let's say high-tech concepts, very strong dynamics in mechanical, in electronic controls, and so on. And if we are able, as industry, to drive the cost of these parts down, that will absolutely allow our customers to find more positive business cases in their industry. So in that way, we are all connected. And the typical challenges in the way for us are focus stability, power stability out of the lasers, position stability over long term, that the laser is a long-term time. Every time is projected on the same area of the build plate, and but also long-term stability in the laser-to-laser calibration, because on the right here you can see this is the conceptual design of our system where we have 4 lasers connected to each other, and actually they should run as one laser. We have dedicated optics in this. We have high resolution cameras, all kinds of concepts to calibrate, but still it's a challenge, it's a struggle to keep everything in control with the different temperatures you can describe. You can create you can identify more than 70 parameters which could influence the stability of this optical chain. And that's actually where I would like to stop with. So to end my presentation with. So if there are any questions, please let me know.
Thank you very much. Goedemiddag, Harry. Thank you very much for being with us this beautiful afternoon. Here in the Netherlands, a bit cloudy, but we are doing our best. From Eindhoven, Rock City, the ecosystem for innovation of photonics, one of the nice locations for having a company Photonics is Eindhoven. And I would like to welcome you. I would like to also thank your previous CEO, Dan Kersten, who made this introduction and made this possible. So Dan, if you're watching us, thank you very much. Harry, you get the epic question. The whole value chain in front of you. You had challenges for them. What can they do for you, and what can you do for them?
If we look to the whole value chain, there are many topics we could like to. First of all, is our end users would like to have a very good predictability of their design. How can that be realized in an AM value chain? So what we connect to is more the Industry 4.0 area where we work with digital twins. We can in the beginning of a conceptual phase of a part design, we already can predict what will be the outcome of that part into a complete manufacturing facility. So immediately you can select technologies, or you can even improve the technologies in a way that you can improve your design to be more compliant with technology. Secondly, when you go to an industrial area, industrial additive manufacturing environment, there it is, and that was also already mentioned by Martin, is the connectivity of our equipment to the post-processing equipment that in a way that you know at the moment you are going to design your part already, is you know what are the design requirements for your post-processing part, but also design requirements for example, for powder removal or for other finishing. So that's a broad scope of topics which needs to be incorporated into the first phase of your process. And that's an area where at this moment a lot of initiatives are going on from many companies where we as industry have to come together. But we're still many let's say activities where still many open endings are really to come to a fully industrial manufacturing chain.
I'm extremely happy that Additive Industries is with us today, because for many discussions with your colleagues in the past, you share the epic vision, which is that photonics is a digital technology, which is what's on your mind, we'll make it real with photonics. We have a question in YouTube about this topic. Nuno Elgar Fernandez is one fan of EPIC. Thank you very much, Nuno, for joining all these meetings. He's wondering whether the unique algorithms used by Additive Industries are somewhat related to new neural network computer vision, or if you are looking for collaborators on this particular part.
I think there's always an opening to look to new ways of specifically software algorithms to help us to do calibration faster. So if neurological networks or AI-like networks, it's on our radar. That's what I can say. I don't know yet what the exact level of that is, because then I have to connect to our optics specialists. But I'm happy to make that connection. So
when in the next quarter we organize a meeting on computer vision, I will be calling you so you can act as an end user there and look for potential collaborators. I'm going to have a couple of people who I think they should talk to you. One of them is from Madrid, a beautiful, beautiful city in the center of Spain. NIT is making weird sensor and weird camera systems for 3D printing process monitoring. Rodrigo, how are you doing today? ¿Cómo estás?
I'm doing fine, thanks, Jose.
What do you think you could do for Additive Industries for AUDI so far?
Well, we have we offer to the industry our advanced monitoring and control tools that can be used to improve the quality of the process. All the systems that we offer are based in high-speed infrared cameras that are built by our own company. Let me share my screen because I have prepared a couple of slides, and then I can show better. What we can offer. Okay.
This was, of course, not planned whatsoever, that we will give you the floor, we share the slides so the potential customers, Additive Industries. Yes, came as a surprise.
Okay, can you see my screen now?
Crystal clear.
Okay, so first we have for additive manufacturing in metal, we offer two kind of solutions. One of them is called Klamir. This is a system that we have built for direct energy deposition processes such as laser metal deposition and cladding. I think in the talk before from AUDI, related with, of course, with the automotive industry, this system offers a closed loop control of the laser power to ensure the quality of the parts and repeatability, for example, for repairing of molds when building the parts, or for example, other applications like cladding of material on brakes, on car brakes. The system is closed loop, and I think an image is worth 1,000 words, and what I'm going to show you is a video. Here you can see what the system is capable to do. So on the left side, you can see a process without control, an additive manufacturing process made without control. And on the right, you can see a control on. with Klamir. So in this case, the part, you can see that during the process, the system has prevented the accumulation of heat, and this has improved the quality of the part that has been manufactured. This video was acquired by our friends of Trump, so we thank them very much. But this is an LMD case, and on the left side, we can also see an example in cladding, another video taken by Laserline. Mm-hmm. One of the advantages of this system is that it's fully compatible with optics from Trump, Precitech, and Laserline. It makes possible the retrofit of some in some systems. But I think maybe what is more interesting for Harry is this kind of camera that we offer. This is a high-speed infrared camera that it's capable to operate at 4,000 frames per second, and it allows to monitor like powder bed fusions and get relevant data from the process, for example, the melt pool geometry, or study the cooling rate. So, for example, in the photo on the right, you can see the melt pool in a PBF process acquired at 4,000 images per second, and you can see that the camera is integrated in the optical port. We are part of a project, EU project called Custodian, and in this one, there is one of the partners is building a closed loop control of the PBF process using our camera. So this is the kind of systems that we can offer, for example, for this application of additive industries. Okay.
There's obviously lots of room for cooperation here, lots of room for discussion. Harry, there's something else I want you to discuss, and there's a company in Epic from Lithuania called DMC. Sarunas, how are you doing? He's smiling. I really love this guy. Sarunas, thank you very much for joining today. I think there is clear partnership here between additive industries and DMC. What do you think? I have you muted. Yes.
Yeah. Hey, nice to see you. So, yes, we are making the software, and the software that handles all the process from CAD import, then process preparation, then handling all the machine control up to the final part. So, and we do some advanced things like multiple galvo control, like from 2 to up to 8 or even more, and some even closed loop systems and so on. I don't know what are your thoughts in that, so maybe we could discuss this after the meeting, but we might be able to have something.
Additive industry has taken software as perhaps the golden fruit, the most important part of a 3D printing system. Harry, do you have still some challenges when it comes to control automation software?
The holy grail would be having a closed loop control of the laser power beam of the laser, actually the melting pool. So the LPBF process it's a heat induction process. And we know that depending on your part geometry, depending on the kind of process settings, you need to actively control your heat induction. At least you need to control your heat induction. Today we do that with a fixed set of parameters, which have limited adjustability in a way. But if we would have the opportunity to really to look in that melting pool and to control the temperature of that melting pool actively in the dynamics of 10 to 20 kilohertz, which that's what's happens in that pool, then we would be have the holy grail on getting a stable process and predictable material quality. So.
Sharing the holy grail is something great that we got at this meeting. Thank you so much. Thank you, Harry, for this. It was great to have you here. The first of many, promise me. Computer vision, I want you there. We have Infinite of Benjamin raising the hand. Benjamin, what's on your mind?
Hello. Yeah, I was thinking about Rodrigo Linares. Thank you very much for quickly showing your technology. And I was wondering, are you just interested in additive manufacturing, or also can we use your technology and adapt it to some welding applications on very low scale? I mean, for us, it's also important to get a feeling about the temperature development during welding. And I was wondering if your technology can make us help to have a deeper look inside.
Thank you very much for the question. Actually, I was just focusing the presentation on additive manufacturing, but we have used our technology, our high-speed cameras, also to get a quality assessment of welding processes. We have a solution where we have combined the camera with a deep learning system and we are capable to teach the system how a defective weld is or how it looks like, and then the neural network is capable to detect that in real time, operating at 1 kilohertz. So yes, I will be very happy to discuss it with you in a separate room, what we can offer you for quality assurance of welding processes.
Thank you. Thank you very much.
Benjamin, look, we started with Audi, then we continue with additive industry. You know where we're going now? We're going to Siemens. We're going to Siemens, Pajazit, Additive. Thank you very much for being with us. You are one of the heroes of EPIC because of the Manuela project outreach that we're collaborating with. And because this stupid virus wasn't going on, we would be having present meetings at Siemens on 3D metal printing. I hope we can do this soon. But Pajazit, thank you very much for being with us today. Tell about what Siemens sees in 3D printing business. The floor and the attention of everyone, more than ever, is going to Siemens, going to you.
Thank you very much. Thank you so much.
I think we need to do this meeting at Siemens.
So,
I was
can
so
you see my
depressed.
screen?
The floor and the attention and the crystal clear presentation is in front of us. Go to presentation mode, just there. Yes.
Yes. Only one moment now.
And we see crystal clear. The way that Siemens intended it. The floor is yours.
Yeah, but yeah, exactly. So, but the small changes we are Siemens Energy now. So this is small changes from the last. Okay, Siemens existing in Sweden in one small town, Finspång, and we are producing the gas turbines since 1913. Today, we have been Siemens since 2003, and after 2020 we are Siemens Energy AB. We are around 3,000 people in Sweden. We are producing the gas turbines. As we know, the material and components for the gas turbines is very specific. There is expensive material, super alloys, and very complicated components. So this is really, really attractive components for additive manufacturing. We have 2 workshops today, one old workshops shown in this first picture, and we have started new one, biggest workshop. So today we have more than 40 printing machines worldwide, and we have experience during 2009. There is more than 10 years, and more than 20 components is today's commercial production, and we have 1,500,000 operating holes in our components. There is a lot of people who is working in our factory. There is more than 150 people, and our plan is to have 200 components until 2025. There is 4 different areas how we are working. This is rapid manufacturing, rapid repair, spare parts, and rapid prototyping. So this gives us very nice benefits. For example, 65% less resource in our production. We can make repair and reducing repair time by 60%, 90% of reducing lead time for spare parts, and in design area for prototyping especially, there is 75% reduced the developing time. Our history started 2006. There we bought one company from England, Material Solution. But here in Finspång, in Sweden, we start 2009 with first M270 SLM machine. And it was only for testing. So biggest expanding of additive manufacturing started 2012, 2030, 2040. There we bought more machine from EOS, from M280, 90, and 400 Quattro. In this time, around 2013, it was the first serial production there is repair of our burner for our biggest SGT 800 turbines. After that, our history began, and we started, for example, like Centrum of Competence, and we start to qualification of different materials. Our material is nickel-based material, actually, so we haven't any titanium, aluminum, or similar. So 2016, we had the inauguration of our workshops. And after that, we started to develop a producing of components like blades and the burners and similar. So 2019, we had started new workshop, which is now in our also production. 2015, 2016, we back to the history, it was our traditional workshop. Exactly in this time, we meet a lot of the problems in additive manufacturing. Our knowledge about material was very low. We haven't really designed culture in our designers. Software was not really good. We haven't education. Machine performance was not really good in this time. Also, the quality was not on the right level, and the environment was not really good for our people. So, if you're looking at the development curve, we was the 2015 on the top, and 2016 we was on the bottom of the development. And in this time, we start to thinking, what should we do standard? So we tend to go from traditional workshop to one connected additive manufacturing workshop by using of manufacturing execution system, IM networking, digital twin, and more software. Today we can say that we have between 60 and 70% is finished. And after that, we start to learning IM workshop by using a big data analyzing, IM monitoring, virtual storage, and machine learning. Next stage is intelligent IM workshop by using robot, virtual reality, augmented reality on the last stage is autonomous workshop. There is the plane 2025 in Sweden. This result of our development is really connected to our cooperation with university, with research institutes, with company with the same area in additive manufacturing in Sweden and worldwide. So today we are a member of a lot of different forums like Arena, Canto, DMRC, and similar. And we have about 20 ongoing projects by year related only to additive manufacturing. We are member is Manuela, European funded project, and there is the focus on automatization of pilot lines for additive manufacturing. So we are working in 4 different areas. That is application, material, process, and digitalization, and robotic. For this conference, I want to show some example what is our benefits. The first one is our burner. This is the typical component for gas turbines, which including 13 different components and 18 different welding positions. So you can imagine how it's easy to put together 13 components by using 18 different welding positions. Today, this component was by using and I can say fantasy of designers to be only one component. And we changed the leading time from 26 weeks to 3 weeks. So next area is nuclear power. There we had made one component impeller for nuclear plant in Krško, Slovenia. And this component is in using, I think, during 2 years. So all inspection talking that the component is reach all demands what they have to need. And the second component is clapper and clapper holder. This is for one nuclear plant also in Europe. And this project we calculated to be finished during next month. From Krško, Slovenia, we have got the certificate for producing of components for nuclear plant, which is really good for Siemens and us. The last is using of robotic in additive manufacturing. The main idea with robotic is to avoid contact of the operators with powder. So we made a lot of tests, and today we can clean the chamber of some of our machine by using of this robot. This is one universal arm which is collected together with AGV, and they are collaborative robots, so they working together with our people in some cells. So in short, it was my very short overview about additive manufacturing in Finspång. I mean, for this presentation, what is our status is 1/2 hour too little time, but
yeah, but you know, Pajazit, thank you very much for your contribution. Now it's time for looking a bit to the future and answering the epic question. So what can you do for them and what can they do for you? Because we saw how you developed, you have these issues with materials that you overcame then a few years ago. Now you put a bit of ideas there, but now imagine you're here with all the value chain. That is not imagination, but is the truth. What would you like to have from them? For example, in a close future, or anyway, something that you see that actually is challenging now?
Yeah. You know, Siemens is the first Siemens is producer for components for own production. As you can see, we had the same program for specific, for example, nuclear area is really interesting for us. There is a lot of policy, how the components should reach the all standards with delivering. So this is really interesting for Siemens. It needs a lot of testing. It needs a lot of time for producing. So everything must be on the time. Everything must be regarding the specific standards. So that is interesting for us. So it is difficult to say. Yes, we can offer, we can produce components for everyone, but especially is not too much time for that. What we need today is more robotic. It is more automatization in our production to avoid this directly contact between the people and the powder, because the powder is not too dangerous today, but who knows? Actually, it's not really good to be in contact with powder.
Now, this is clear, sure. So this is basically also, so you started already to test some of them, right? So you show us in the slide.
Yeah, we start, but this equipment we can use only for one specific kind of the machine. As additive industry, they have gone more in this position. So I like this solution which they present. So in this direction, I think the additive, the machine for additive manufacturing should go. Post-processing is also very interesting thing for additive manufacturing, because you know the tolerances and the surface quality is not really good as the designers want to have. And there is also the big question for them when they start to design component for additive manufacturing. The question is always, yes, but you cannot reach this design, this tolerance, this surface quality. So there is our strategy to go more in this direction.
Okay, very good.
Yeah, so, there is as in our development curve, I talk about the machine learning. We need more. That machine should take the same. The machine should take decision when machine should stop, when machine should continue a work. Is that right time to be, for example, no, I make wrong, this component is not good, or yes, I can continue without people. So more intelligent additive manufacturing.
That's a really nice list. So you see, Pajazit, you didn't write it on the slides, but you had a nice shopping list. So it's really important for us to know that there is also already some same perspective also with the companies that are sitting here. So Henry, maybe you want to comment about the robotics and about the overlap with Siemens demands. Harry? You are muted. Additive Industries. Don't look on the other side.
Yeah.
Yeah, there you are.
But, could you, because also my speaker was a bit muted. Could you repeat the question, please?
No, he was just that he was commenting that when they need robotics, so these new robots and automatization of the systems is the way you are taking, and so you were saying that is that. So I wanted to say if you have a comment on this and if this is a common way to go.
Thank you. Sure. Is my camera? You can
yes,
see
he's
me?
on. Yeah, we can see you.
Yes.
Okay, very good. No, thanks. There were some topics on the computer, at least appear to me. Robotics in a fully automated chain. Actually, you would like to have the parts, let's say the parts extraction from the machine or separation from the machine in a setting where you have a complete where you have an automatic guided vehicle actually transporting that to another station. Actually, you should then have a completely virtual factory where you have a number of functions available, from of course the part printing to the part processing, post-processing, which could be a number of technologies. And actually that should be, in an ideal situation, that should be a completely virtual environment which you control. You bring in your part, and hopefully, and in the ideal case, this the software algorithms calculate for you the most efficient and effective way to process that part. That would be the way we see at how this technology should evolve, because once again, post-processing is needed. You can include a number of post-processing steps into the AM machine, which makes sense. But at a certain moment, you're working, if you would introduce too many complicated, let's say, post-processing steps, you get the question of load balancing, because the speed of the process is still slower than the speed of most post-processing options.
Yeah,
so
this we heard this is a problem. So let's not be too slow, otherwise.
not that always, because there are also post-processing steps. It's really application dependent, where you, for example, if you print things like medical implants, small parts, but you can print them a lot on a platform. And when you look to the total post-processing times of those parts per piece, then it exceeds the printing time in itself. So that's it's really it's a per case a balancing act, and it's very interesting always to dive into this kind of problems with your customers, with this kind of, let's say, complete value chains, and trying to optimize those.
Very good. So that's really, we are here for this. And so now we have 2 comments. So the first one, well, 3 comments. So now this, the floor is on fire. First, I would like to give the floor to Yves from 3D, Aconity 3D, that he asked me in private. He wants also to comment on this. So Yves, can you do you hear us?
Yes.
Yes.
For me, I try to unmute my phone. So, yeah, from my perspective, we as Aconity 3D also a machine manufacturer for 3D printing equipment, powder bed-based systems. And Harry nailed it, I believe, because it really depends on the application, and that is the most crucial part. So we heard from Siemens that a more intelligent machine would be awesome, also more robotics, so that you don't get in contact with the powder. The question is then always, and that needs to be solved with the final customer like Siemens, what is the application? What is the material? So there are already certain algorithms also in our machines which allow the machine to counteract on certain defects during the process. However, that differs from a standard aluminum process compared to a steel process compared to an Inconel process, right? So my question back maybe to Siemens, is there knowledge within Siemens, so to say, to bridge the gap between, well, let's say my sensor senses that the melt pool is too cold. Does Siemens have for the specific material in question the parameter back off, so to say, to know, okay, if I have 30 degrees less temperature, I need, I don't know, 20 watts of extra laser power. Is that gap already bridged, or is that something you would expect artificial intelligence, so to say, to jump in and fine tune those parameters? That was to Siemens.
Pajazit, this was the question for you? Yeah.
Yeah. I'm not really right person to give this answer. This is more advanced. I can, but I can say, yeah. We are only for our material, nickel-based material. So there is the practical knowledge which we have in our factory. Yes. Siemens have developed also a lot of the software which we are using today, like I'm monitoring in our machine. But we have a very good contact, and we are going through our supplier. In this case, is good cooperation to solve all these problems.
Mm-hmm. And in case you want a new contacts, Pajazit, you know, you can always ask Epic, and you can ask Yves and all the people here. So do not forget to use your network and your Epic connection, so that we can always put you also with new contacts in a really nice connection. So let's not forget that.
Okay. Yeah.
And now we have also Christian from Optoprim, right? So you raise your hand, please. Ask your question.
Correct. Yes. It's not like a question. It's like, a point where Siemens was pointing to that the intelligence of the machine is very important. And we have kind of a new sense we can give to the machine. It's not like a thermal sensor. It's an acoustical sensor where we already tested in different powder bed machines. So you hear to the continuous process and get back as feedback the intensity of the functionality of the laser beam within the metal. So it really can monitor during the process if there are interruptions, if there are changes in power or the whole process in general. And it's quite small, super easy to integrate, and maybe the new sense, besides maybe the eye, the temperature, maybe some feeling, to give to your machines. And I'm happy to share some information who is interested to this kind of new sensor in the AM field.
Very good. So we have the address for Optoprim now too. If you need, not only Siemens, of course. Anyway, so now I guess we maybe keep going, and then we give the floor. Ben then had a question. So then it was a real question. Yeah, please, Ben.
Yes, short one. Maybe to Additive Industrials. Thank you for your nice comments. And yeah, I've been last week close to your area, and I can feel the energy that is going on in Eindhoven, around that area. But I'm wondering, so what are you think are the challenges? What kind of future sizes we can achieve, and how is the reproducibility? And you pointed out that example for ALSM, like where you had the positioning on top of the silicon wafer. How long roughly does it take to manufacture such a piece? And if I want a second one, how good can you reproduce it already? I mean, just for me to get a little bit feeling on what's possible and where the limitations are.
Oh, these parts, I think they are about. It was in an article. So on average, you would produce such a part when I work with 4 lasers. I just now did 2, but I could work with 4 lasers. Then you would have an overall build time of 20 hours of the whole build, but it's then 5 hours per part in laser time. So that's let's see, 5 hours per part on average, or average throughput time. The dimensional accuracy of these parts and the material properties are fully within the capabilities of this process. So that's not we needed to achieve a certain density and certain homogeneity, and that was all perfectly done. If you want to start such a job once again, it's literally the press of a button. Of course, you need to supply some powder into the system, which is also done automatically today, and then it's automatically filled, and you enter the build plate, which is automatically positioned and adjusted, and then you start the print job, and you can just run it to full functional production.
Okay.
Full series production. Yeah.
Very good. So now let's give it for real the floor to Martina. So thank you very much for being here from BEAMIT in Italy. So the floor and the attention of everyone is yours. You're still muted. Now perfect.
Can you hear me?
Sure. Yeah, we do. There you go.
Let's go in presentation mode. Okay. Hello, everybody. Thank you, Francesca, for giving me the opportunity to be here today with you discussing about the latest challenge in metal IM. I'm Martina Riccio, and I'm currently leading the R&D activities of BEAMIT Group. My background is mechanical engineering, and actually, when I was a student, I fell in love with lasers and laser technologies, so I decided to focus on them. I started with a master thesis on laser metal deposition by wire, and then I joined BEAMIT 4 years ago and focusing on laser powder bed fusion processes. So I started with material and process development and optimization. Then I led the material and special process team working on process procedures for customer international standard requirements. So let's have a brief introduction to BEAMIT Group. When I started 4 years ago in 2016, we were only 20. And now, as you can see from this slide, we are more than 100. And this is because in the last years, additive manufacturing had a very fast growth, and our management and our team work strongly in order to be here today, one of the biggest solution providers for IM in the world. We are now in 5 plants, all located in a region of 40 kilometers in radius in one of the most industrialized part of Italy, that is Emilia-Romagna. BEAMIT has some shares in Pre6, that is an innovative startup that is focused on post-processing for IM, such as depowdering, heat quench, and super finishing processing. But also in the last month, Zare, that was one of our major competitors in Italy, has been acquired by BEAMIT and is now part of the group. Also, last year, from July 2019, Sandvik has some shares in BEAMIT, and this means that with Sandvik we can cover the whole value chain, starting from metallurgy and powder up to the final component. We have now almost 60 additive manufacturing systems for metals, but not only, we're working also with polymers and ceramics materials. We are now able to process stainless steels, aluminum alloy, titanium alloys, nickel-based superalloys, and all these materials are completely qualified and in production for different sectors like aerospace, automotive, IGT, or biomedical. But also, the additive manufacturing is a very fast-growing technology, and this is why we are investing a lot in R&D, especially in new material development. And for example, in the last years, we focused on high-strength, high-temperature aluminum and titanium alloys. So let's see what, according to us, are the current challenges of metal IM. And first of all, it's material, because as you can see, our customers are now even more confident to the technology, and this is why they are asking us always more new materials, and this is challenging. This is challenging because today most of industrial additive manufacturing machines are equipped with near-infrared fiber lasers, and there are some material like pure coppers or aluminum that has high reflectivity to this wavelength. So this is a challenge, and can a green or a blue laser be the answer to this problem? Then another challenge that we see is the non-weldable materials, that are all that materials that for metallurgical reason during the process and during the cooling phase of the process generate the so-called cracks. And in this way, can the laser, a different way to manage the laser power and energy, be the solution for avoiding this phenomena? And last but not the least, or maybe the most important one now, is the productivity, because up to now the increase, the process is still very low in productivity, and the increase of productivity has been managed by the AM machine supplier, putting different lasers working in parallel in the same process for achieving an higher build rate. But what if there is a faster or smarter way to achieve this kind of higher build rates, maybe using different size of lasers or of beam or B-shaping technologies? Because now the laser that we are using are laser with a spot that is 100 microns in size, and you know that this is very small spot size for a massive process like the AM is. So one idea could be to use different beam shaping or sizes. For example, using the biggest one in the core scanning, and then to move to the small one in the contouring of the small picture. So these are the main challenges that we are now looking on the metal IM. And what we offer is that we select among our machine parts, one of them to be completely dedicated to R&D project with very low TRL. So it means that we select one of these machines that we want to transform in a kind of Frankenstein machine, putting different lasers or optics, hardware, printing system, and everything, just for testing them and to do this kind of R&D activities that are custom driven, because we know which are the customer, the market requirements, and this is why we think that we are able to conduct a kind of R&D activity that can be in the future very easy to scale for the production. So now we are looking, I'm very happy to be here with all this audience, because we are looking for partners for this kind of R&D activities. We are looking for joining consortium for participating to Grand Call, and we are looking for other ideas or solutions to develop and test together. So that's all from my side. And thank
Martina,
you.
thank you very much. Grazie mille for being at this meeting. Indeed, BEAMIT is one of the success stories of Europe. If you're looking forward to joining consortium, I would like to recommend you to join the biggest in the world. So this could be actually make a lot easier to make the connections with the companies. There is a lot of room for cooperation. Thank you very much for sharing the challenges that you're looking for and what you can provide. I really love that slide, and I would like to remind everyone that this is what this meeting is about sharing your challenges. And here it is what they really told us they want to do, a Frankenstein machine. When it comes to this Frankenstein machine, there is a couple of companies which I think can help you with. In a previous meeting, we had a presentation from Aconity 3D. And Aconity 3D had a very interesting process in which they could actually use two different materials into the same 3D printing process. Yves, are you with us? I think I took a risk.
Now I am, and I'm not. Can you hear me?
Yes, loud and clear.
Yes, yeah, I know this issue with Frankenstein machines. We also have customers who have those because they find an old laser in their basement or something, and they say, okay, let's put in that laser, and hey, Aconity, you are a special machine manufacturer, can you make it happen? And that's what we call Frankenstein machines, so where different parts and bits and bytes within one machine. But yeah, Jose, you're right. We have developed this multi-material part which can be integrated in one of our systems, and that is actually that has been developed by a project partner of ours called Aerosint, and they can most likely help you if you want any multi-material options for your machines as well. So, however, that is more based on powder bed fusion, so not a typical beam approach, I would argue. But anyhow, solutions are out there. So if you want any help in implementing any Frankenstein parts, just reach out to me later on, and I'll be more than happy to start a conversation with you. And let's see if we find any solutions for your problem you have here currently.
AUDI, Siemens, Infineon, I hope you were listening. Aconity 3D has a process to 3D print two different metallic materials in the same process, in the same machine. It's quite spectacular. A great room for cooperation. Also, Martina, you're looking for partners in European projects, right? Next year, we have a call for green manufacturing. And there is a company in the room who registered last minute, and they do green steel making. Juha from Sapotec, thank you very much for being here all the way from beautiful Finland. Juha, what is green steel making?
Yes, of course, that's a good question. We at the Sapotec, we have been developing photonics solutions for steel making, and as a metallurgist working in steel mill, I was always looking for new solutions, and as there was no companies who will implement the solutions to steel mill, we established a company to implement the newest photonics solutions, photonics innovations to steel making, and we have been doing this very successfully. We have a big company supporting us to sales our systems, but we are all the time looking new innovations which could be implemented in steel mill. Steel mills manufacture steel for AUDI. They manufacture solutions for laser manufacturing like you are doing here, and it's interesting to see what you are doing here for this sector and what we can implement maybe to the steel mill. So anybody who thinks they have a solution which could be beneficial for steel mills, we are interested to participate in any consortium related to steel, green steel making and metallurgy at all.
Thank you very much, Juha. Martina, there is obviously room for cooperation in every single field. We have also companies like Lasea that they make fantastic equipment. Jose from Lasea, how are you doing? He's smiling. I really love this guy. Jose, what do you think? What kind of cooperation can you do with BEAMIT?
I was thinking you will invite me to talk. I don't know why. I think it's a good opportunity. Thank you very much, Jose, because indeed, Lasea is more a subtractive company than an additive company. And I have listened a few times in the last hours about finishing. We offer very accurate machines able to work on 3D parts with ultra short pulsing lasers, femtosecond, and so on. And well, we can carry on different operations on the surface. We can polish, but we can also functionalize. And we will be very happy to collaborate with all of you and see how we can put all together to achieve it to our next level. We also have an activity on machine learning for our subtractive processes that maybe can also help in other areas.
Martina is the R&D manager of BEAMIT, our entry point to access one of the success stories of Europe. Martina, we are going to be sending a lot of emails to you with potential cooperations to enter partnerships. Thank you very much. Grazie mille for being with us in this beautiful meeting. Shall we continue, Francesca? Let's continue. Let's continue this great meeting, and we go now to the company in laser that always makes a difference when it comes to high power, Laserline. And we have with us Steffen Bonss, the senior technical sales manager from Laserline. Tell us how we build all these companies, how we build something that we can actually all work together. The floor and the attention of everyone goes to Laserline. Let me do one. Let me see. We have one more chance. Yes. Laserline, the floor is yours.
Yeah. You see, it's not necessary to make a test. We made a successful test, but now we missed the success in the first step. Okay, now I need a second step and a third step. Anyway, it's about heat treatment. Heat treatment with our lasers is an old history, and even heat treatment with lasers is in the laser world is a quite old history. But in a heat treatment or in the hardening technology world, we are still newbies, even since we offer heat treatment since more than 20 years. Anyway, we can do the heat treatment not only at solid parts. Solid parts means standard manufactured parts. We can also do the heat treatment in also, of course, on additive manufactured parts. And so there's no difference in principle. The problem could be that the materials where we made the heat treatment or the hardening with are hardenable materials, and additive manufacturing of that kind of materials might be a little bit a problem because the risk of cracking and the high carbon content. But anyway, if you do maybe the additive at elevated temperatures that you can manage it crack-free, then we can, of course, do a local heat treatment for softening or even for hardening afterwards. Anyway, if I speak about hardening, it is a heating process, first step, to a certain level of temperature, depending on the material. And then we have a quenching. And the quenching happens, in that case, by heat flow into the cold part of the cold part of the whole part. So we make just the surface heating and then heat flow rapidly into the complete volume of the part. And this is the most effective quenching what you can have. So it's better than any liquid quenching with light and frost phenomena and anything. So that's why we can even do a hardening at low level carbon steels. Low level means maybe 0.15% of carbon. We can get the max of hardness what's possible with these even low content of carbon. So that's very specific for laser. And the other very specific for laser heat treatment is that we can apply the laser very locally. That means we do just the heat treatment where it is necessary. And the overall heat input is down to the minimum. And so at the end, resulting distortion is down to the minimum. On the other hand, the absorption of the laser depends on the material, depends on the surface condition of the material. So if you have a very shiny part, steel part, then you have 40% of absorption. If you allow the oxidation, then you have 80%. So that makes the difference. If you do a post-treatment by milling, grinding, whatever, you can usually allow the oxidation and you have a very, very high efficient process, allowing the 80% of absorption. And even the measuring of the process, the temperature measuring is very highly efficient because any pyrometer or camera-based system can measure with an emission coefficient of 0.8, 0.9 with a high accuracy, these high temperatures. And so this heat treatment is a process what can apply it locally, high efficient, and with low distortion at the end. And it is always running, we heard this topic today, as a closed loop process. We always measure surface temperatures with pyrometers or camera-based systems, and we give the signal to the laser power to keep in a closed loop the surface temperature constant by controlling laser power. On these images you see on the left-hand side, a camera-based image what happens during laser beam hardening of turbine blades. Maybe it's a Siemens blade, I'm not quite sure. The center is of sure a Siemens blade. That's I know from the shape, and even the cross section on the right side is a Siemens blade. Steam turbine blades for big power generation power plants. And we need a local hardening at these blades for avoiding a droplet erosion. And this is just an example for what the laser can do. Very local heat treatment on these parts. We need the hardness just at the tip, and we don't need an elevated hardness in the very ductile root of this blade. And what we need for doing laser hardening for most parts is a very well adapted shape of the beam. We don't necessarily have a round spot for laser hardening. And sometimes we need a rectangular spot, but in most cases we need some flexible adapted spot in size and intensity profile. And that's depends a little bit on the processes. Sometimes we have processes, you see the center, where a rectangular spot is sufficient. We apply 2 rectangular spots to harden a tooth of a tooth rail. Shot by shot, tooth by tooth, 2 simultaneous applied spots, shot by shot. And the customer has different sizes of his rails. And so we need just a rectangular spot, change in size. That's what we have. But sometimes we need an intensity profile, what is changing from left to right. And that's what we don't have so far. We have some systems from Fraunhofer where we can do that with a scanner, but they are limited to 6 or 10 kilowatt. But maybe in the future, we will apply our 20 or 40 kilowatt lasers, even for such processes. And that's what we would need. Beam shaping systems, flexible spot shaping systems for elevated power. That's a lack what we have so far. Let me speak backwards a little bit about the principles of laser beam hardening. The classical process is a feed hardening. That means we have a certain spot moving over the part, or this part moving under the spot. The second, what I already mentioned, is single shot hardening. Maybe a spot applying to the part, on, off, done. And the third version is maybe rotating a part very fast, applying a spot, generating a hot ring by these fast rotation of the part. And with these hot ring, we make a local hardening of a ring, or even local hardening of a cylindrical shape. These are the 3 main principles of laser beam hardening processing. Here you see some examples from hydraulic, from automotive industry, or even from machine industry. And I already mentioned the advantages: less distortion, no quenching liquids, high productivity, because we can integrate that nicely into production lines. But we have also some disadvantages. We are limited to a penetration of 1.5 millimeter. This is by this self-quenching. If we let the heat flow deeper, we don't have the conditions for self-quenching and the surface of the part. So that's are the limits. Sometimes we need to change. If you want to replace an existing technology, we need to change the material. For instance, case hardening requires a low carbon material, what you put the carbon in to the part during the process. But with a laser, we need the carbon in advance being in the process. So we need to replace or change the material. And that's sometimes a problem in the manufacturing, to change material. And on the other hand, despite we do laser beam hardening since over 20 years, there is still a lack of knowledge about this kind of technology in the heads of all the manufacturing designers and or manufacturing guys, because they all think in standard chains or production chains, soft machining, hardening, hard machining, and they don't think about the integration into the line. But this is an option what we have with the laser, of course. Let me come to the what we need and what we have slide. This is my last slide. Okay, we have some for specific geometries of the laser spot for applying for laser hardening. We have some optical solutions. Rectangular spots are done. That's what we have. Zoom for rectangular spots are done. Ring-shaped spots or round spots existing. But we don't have 2D intensity profile changing, size changing spots for powers over 20 kilowatt or over 10 kilowatt with a scanner or whatever flexible elements. That's what we would need. And we would in general need some optical elements for very high powers up to 50 kilowatt. Most of our systems running to 10 or 20 kilowatt. But maybe for the future, to have a larger areas, what we need to treat, we would need optics, optical coatings, what would withstand these very, very high powers and high intensities. And so the accuracy, what we need, and for the machining, for the laser processing, this is done by standard CNC machines or even by simple robots. So the accuracy is sufficient. This post-processing is another topic that would be nice to have, depending a little bit on the manufacturing. For single part processing, it would be nice to have. For mass production, it's not necessary because you once do the programming and then the machine does the job day by day, 24/7, it's no problem. And the machine design and shielding gas application, I mentioned oxidation allowance or no oxidation. So if we don't want to allow the oxidation, we keep the parts clean, and we need to apply shielding gas like nitrogen, but these devices are usually individually designed, so that's not really a problem. And the customer can use the advantage of having clean, non-oxidized parts out of the process if he needs that. For some examples in production of hydraulic parts, our customers do the process in shielding gas because they don't want to do any post-treatment, post-grinding or whatever, and they can do that in that way. So that's not a problem. But what we would need is very, very high power optics and flexible optics for these high powers above 10 kilowatt, 20 kilowatt. And the optical coatings, optical materials, what could withstand these very high powers and high intensities. Design of the final optics and the water-cooled cases of the optics, that's what we have as a competence in-house. But the optical elements itself, there we are a little bit limited at the moment to the properties of glass, properties of coatings, and all that. So that would be maybe something for the future, what we would need. So thank you for everyone for listening, and I'm open for questions or suggestions how to proceed with these optical elements. Thank you.
Thanks a lot, Steffen, for your contribution and your detailed list. So that's always good to have it. So let's unshare your screen so I can do it as well. There you go. So then it's finally a nice, opportunity now to discuss together how we can help also Laserline, especially for the optics. Is there someone here who wants to comment on this? Because I see you're a bit shy.
Maybe we can help Steffen to design these specific optics. Of course, we need to set up somewhat more requirements, but yeah, I guess we can do something.
Yeah, I can make the connection to our developers.
Yeah.
Maybe can you, Frank, make a couple of comments about what is NTS Optel doing, so that we contextualize a bit the offer?
Yeah, sure. NTS develops, it's a first-tier company that develops, basically all kinds of optics, mechatronic systems for end users, OEMs.
Mm-hmm. Yeah.
Very good. So then now we of course can also connect you later on, and that's the best thing we can do for you, of course.
Yeah,
then
sure.
Are there other questions or other comments about optics? We have here some experts also about the lasers.
I have a question for Steffen.
Yes, sure.
Okay, Steffen, is it also possible to do some, let's say, surface, retreatment? You know, from one of the characteristics of the AM processes of powder bed laser fusion is that we have micro cracks on the surface. So specifically regarding fatigue properties. Usually in fatigue-prone applications, you need to do hipping or shot peening or anything else. But would be a laser treatment an option to do to improve parts characteristics in this respect?
In principle, yes.
Mm-hmm.
But it depends, of course, on material and shape and anything. So if it would make sense to do any maybe a remelting, local remelting to do the melted cracks. The question is, what happens on the borders of the remelting zone? Can we do the remelting zone that the borders are in an area where we have less stresses? Or we can do a kind of a remelting embedded in a heat treatment process that we don't have so much stresses and can be to reduce the stresses. But in principle, this is what the laser can do. Very local, maybe not the whole part doing in the hip, but at a local area, we can apply the laser doing some heat treatment, remelting process. If the cracks are still existing, then of course a kind of remelting would be necessary. Otherwise, it will not get linked together. The question is, after a melting process, you have tensile stresses in the surface area or to the side. And the question is, okay, how do we handle that? But as I said, in principle, yes.
Yeah, but it could be a combination of simple heat treatment with some local local treatment with a laser, and finally, it's just looking to the fit for purpose from a fit for purpose approach instead of really the horsepower, because hipping in itself is also not a very cheap technology, and it also increases often the lead time substantially. But
with laser, we could do it probably much faster. That's it.
Okay, thanks. Interesting.
Very good. So now it's really time to go maybe to look at the future. So last talk always looking at the R&D and new developments with, of course, a lot of experience behind. So I'm really happy that today we have a shared contribution by SINTEF. And so we start first with the digital expert, with Thor. And then we will have Klas also talking about a bit more the technology in general of additive and advanced manufacturing. So I don't know who wants to share the screen, but I know that you have a deal. So the attention goes to SINTEF, and Thor will start. Thank you very much.
Okay, this is Thor Dokken. I come from SINTEF Digital, and after slide 3, then Klas Bebe will be the guy that will be speaking, and he's come out of SINTEF Manufacturing. SINTEF is like the Fraunhofer of Norway. Compared to the size of the population, we are similar in size, but Norway is much smaller, so we are just 2,000 people. So, SINTEF vision technology for a better society, and this is somehow the modern way we present ourselves. We work with industry, we work with health, we work with smart society. We do a lot, but additive manufacturing is somehow cutting across here. So there are many aspects of additive manufacturing that we address from different perspectives. Then where do we find additive manufacturing in SINTEF? So we have different institutes with different names. The names have been modernized. SINTEF community, there you find AM in construction. In SINTEF industry, that is composed a lot from chemistry and materials research, you have AM and materials. And also like catalyst design. Then where I come from, SINTEF Digital, it's AM and digitalization, the mathematics, we need all of that. Then you have ocean, that, okay, we got 40% of the continental shelf in Europe. So we got a lot of ocean, so there's a lot of activity there, and they use AM for different purposes. Then SINTEF Energy Research, as you know, we got a lot of oil and gas activities, and there's a lot of use of AM in that area. And then you got SINTEF Manufacturing, that is more focusing on the additive manufacturing process planning. During the last years, we have had a lot of cooperation between SINTEF Industry, Digital, and Manufacturing with respect to additive manufacturing, and somehow looking at this from different perspectives of the different research fields. Then AM and digitalization in SINTEF. So I come out of more the mathematics side. How do you represent geometry? And if we look at traditional CAD boundary representation, you just represent the surface. Additive manufacturing also needs the representation of the inside. Then we talk about VREP, real mathematical volumetric representation. That we also have done a lot of input during the last years to STEP ISO 10303. Then also looking at new ways of representing voids in a structure, and also better connection of geometry and simulation. Somehow, this is some of an illustration coming out of the prior EU project I cooperated called CAXMAN, Computer-Aided Tools for Additive Manufacturing. Somehow we got an STL wall. You have the CAD design, you got material, then you put things into AM process planning and you don't get information back. It's so hard today to update your CAD model because actually what you can somehow represent in traditional CAD is not representing what you do on the AM process planning side. Then I will end with just mentioning two innovation actions that are of interest here. I coordinate innovation action in I4MS called Change to Twin, where one of the areas we focus is digital twins for additive manufacturing. In this, we will have open calls for experiments from small and medium-sized companies. In parallel, there is another project similar with open calls for experiments called PULSATE. That is within the topic of advanced laser-based and additive manufacturing. And the web page will be soon up and running there. Probably it will be pulsate.eu, but I don't actually know. So for small, medium-sized companies wanting to do something, experiment here, contact Change to Twin or PULSATE when that is coming up. And then in Horizon Europe, I looked at the first glance at some draft work programs, and it seems to be a lot of interesting stuff that will happen on additive manufacturing. So then I leave the mic to my colleague Klas Beve, and I click to his first slide.
Okay, thank you very much, Tor. Thank you very much, Tor, and I have complete trust that among your many skills and extreme expertise includes that you are a most brilliant slide changer. Well, good afternoon, everybody. I'm sorry to be the last one. I'll try to make this light and easy for you. I'm going to tell you a little bit about what we have been doing, what we're looking forward from the process and materials industrialization perspective, additive manufacturing. What we need now, additive manufacturing is presently in a situation where it's developing as industrial process. We are industrialized in this, but to do this successfully, we need to have the functional intellectual infrastructure for AM in industry and all society. There's a great need for knowledge. People need to learn things, both the potential users of AM technology, but also the potential customers. People need to know what they can expect from an AM part and also a little bit how to do them right. So the most important thing is to figure out what are you going to do with AM, because AM is not the solution to every manufacturing problem in the world. There's many things. You will still do casting. People have been casting metals for thousands of years and will probably do so for a long time on. And there's also machining, milling stuff. That's good. But then AM has a niche. You can do things with AM that are more beneficial than any of the other methods. But what to do when you know what you're going to do with AM, you also know the why you're going to do with AM. What are the benefits of using AM? And then when you have these solutions, then you can look to how will you use it with AM? How will you integrate this in a process, in a production chain to make this whole thing work together? But besides this knowledge building, there's also need for structure. All over the society, we need to develop legislation to handle AM. For example, IPR issues and the responsibilities within the AM process. Who is responsible for what? Is it the designer, the one who produces the part, the feedstock provider? Who is responsible for the success and the reliability of the part? We need to figure that out. We need to have that clarified. There's need for regulations. How can we handle trade regulations? If you have made a design and then actually basically export the digital model somewhere else, well, in that case, is that export? And how is that with duties and fees and all those things? And then how do you certify? If you have made a design and you send it off to build somewhere, who can you be sure that it actually will keep the quality that you expect? Can you be certain that, let's say you make a spare part for an airplane, you better be very sure that that spare part actually works and fulfills all the requirements. But to be able to do this, we need to look into standardization. That actually build an international, coherent and coordinated standards that will be the same all over the world to make this fit together. And that's a big challenge because AM is a cross-disciplinary field. It covers things. Now we are from photonics, there's laser worlds, but it's also connects to material science, different process, different types. We have people from welding background, people from powder metallurgy background, people from polymer background, people from CNC milling background, and they all have their own systems of thinking and using. And we can't apply all of them at the same time. We need something that's coherent and coordinated for AM. And that's something we're also working on at SINTEF. Next slide, please, Tor. Oh, thank you. So something that we started on working on quite early was making process integration. And it led up that we developed a hybrid manufacturing cell. This was actually a functional prototype that was finished development in 2014. It worked very well. We had a powder bed fusion laser beam machine, which integrated and in collaboration with the 5-axis CNC milling machine. The meaning with this, that we did this, is because both of these technologies are very different, as people have been talking here lots about post-processing. But the requirement for a CNC milling process and the AM process are very different. And to make both of these machines system works in a good way, you better let them do their job the way they do it best. But then, of course, in the same part, there are different sections that maybe are better to mill, and some sections better to do by AM. And then of course, if something is better to mill, then you should mill it. And if it's something that you can't do with anything but AM, then you should do it by AM. But to have this work together, you need both have the electronic information, all the digital information actually able to be coordinated, and also you need something as simple as having the same coordinate system in both machines, so you don't have to sell it about. So what we did work here, we had a generic pallet system, universal 0 point following the part in both machines, but the workpiece was moved manually, at least in this case. And then of course you could download the position and coordinates, and we reached a level where the greatest difficulty in precision was actually the CNC milling machine, the stability of the mills in the CNC milling machine. So we actually needed to put some extra oversize in the parts, in the AM parts, to be able to mill it with good precision, which is quite a nice result. Next slide, please, Tor. But looking at the whole thing, we need to be able to have, as people talk about the entire process chain, we need to keep that in mind. It's been mentioned by many companies here. And to do this, we need to have a specification of the AM-enabled process chain. And the need for this is that the industry wants their first-time right production and reproducibility. When you start your build, you would like to know that the part that come out will fulfill the requirements. And there are several technological keys to this. We need to first specify the process, to have specification of every item in the process parameters, all of the variables as such. We need to have a clear specification of the material, both the material in the final part, but also the feedstock, the requirements for the feedstock, the requirements and the acceptable variability in the feedstock to be able to reach the material quality in the final part. Then you need to put up together the optimized process route, and it is not always the same for all the different parts. So we need to have AM and a complementary process based on whatever geometry and what final application and the specific requirements. And the specific requirements for each sub-process in the process chain. To actually talk about input and output. This needs to be complemented by in-process monitoring, possibly integrated non-destructive testing and documentation of all the key properties to verify compliance with the specific requirements. So we need to have this in control of every step of the process chain so that when you have the part out, you can check that everything is right. You can go back, as Tor said, you have this difficulty of knowing what's actually happened, but we need to do that in a physical world too. And that will be completed with data monitoring and evaluation statistic process control. Now, next slide. I think this is the last one. So I'm also making it. So there is a great vision we had at SINTEF when we talked about this a couple of years ago, and particularly the energy sector was quite interesting. Talk about digital production, integration with additive manufacturing. We look at the pilot solution for a digitalization in manufacturing. So talk about having a digital product warehouse and a feedstock material data with variability. We have those, for example, spare parts, but also parts, real parts and products, and also repair. We make sure there is an integrated manufacturing solution, AM-enabled processing, different type of AM machines in combination with other machines, working seamlessly, following the model of the hybrid cell that can produce parts. But during this manufacturing process, we do have this online monitoring. We have the parameter settings, we have the results, NDT results. And then from the parts that are out in the field, we can get feedback into the system and compare them to the results we had of the manufacturing chain. And eventually go the feedback to actually see, is this well adjusted with the feedstock? Is it well adjusted with the parts, the design modifications, to have this all in an integrated solution? This is the vision we'd like to work towards. And of course, SINTEF is very keen to, it's a research institute, as Tor said, we live by having funded projects. And I think SINTEF is very interested in collaborate with anybody.
And the vision of being a pilot production is fantastic. The pilot production that SINTEF wants to enable is a paradigm shift for the industry. The European Commission has given you some of the taxpayers' money to make this happen, so the responsibility is in your shoulders. We want any company in Europe who has a challenge on 3D printing to contact Dr. Francesca Moglia, who is the dissemination manager for the PULSATE project, and we are going to make sure that SINTEF is positioned as the pilot production for 3D printed prototypes. It's going to be a fantastic next 4 years, Tor and Klas, and I would like to thank you very much for this. For this vision, Tor and Klas, one key question: what is your preferred future, and which companies are really going to help you get in there?
Tor here. The company that is really pushing this replacement spare part, that is Equinor, the big oil company. And they are in the process of putting up the first digital warehouse. And some of the new oil fields, oil and gas fields, they will have a lot of, not have physical spare part, but a lot of the parts will just be digital. So there is a very big push on this to save money, to replace very, very expensive spare part warehouses with digital warehouses and on-demand production.
Any company who has, so yes, please, Klas.
Yeah, I just want to say Equinor is great because they're the user. They can create a pool for this. But we need, of course, we need companies that are willing to work with us for the push too. So there will be a push-pull situation here. And of course, I see within this Epic network, there are several companies who would be very well situated to participate in this. So let's see this as an open invitation to think about how we can make more and better project in Europe on this with Horizon Europe coming up.
You have a big responsibility in your shoulders for the next 4 years. And this, I want to reiterate what Klas just said. Any company in Europe who has something innovative that is looking forward to industrialization, and they can really help making new prototypes from the industry, you can talk to Klas and Tor, because they are the hub to making sure that this 3D printing technology, whether it is for optics beam shaping, whether it is for temperature stability, with these M-Weir cameras for process monitoring, you need, Rodrigo, you need to talk to Klas, you need to talk to Tor. Let's close the meeting here with 2 things. The first one, it has been an amazing meeting. Oh my God, such a great meeting. Lots of room for collaboration, which is what it was all about. Challenges. We talk about the challenges on speed and process control with robotics by Siemens. We talk about the machine vision software for additive industry and their need for closed loop monitoring. There's going to be lots of interaction with that. We also talk on AUDI with the need for processing. We also talk once again for the challenge on stability with focus, power, positioning, and long-term stability. BEAMIT gave a fantastic presentation on both the near-infrared laser with high-reflective materials and the non-weldable materials. They are looking forward to material challenges with the supply chain. And the beam shaping for laser hardening, that was perhaps the best presentation today. Thank you so much, Steffen, for this. They are talking about, they are needing optics for beam shaping, both in the 2D profile as well as the CW over 20 kilowatt laser. The future challenge, I read between the lines of all of you, the future challenge is a multi-beam system with blue-green laser sources. It's going to be a fantastic road ahead to build towards that particular challenge. I just would like to say that this is making my dream come true. I really want to continue doing these amazing meetings. I really want to continue working with all of you. I just would like to remind you that if you want to be truly successful in these meetings, the success is in the follow-up. Just make sure that you want to get in touch with any of the participants, send me an email, jose.pozo@epic-asoc.com. I will be more than happy of making this introduction. Most important is that now we have one-on-one meetings in the room. So all of you in the Zoom room, you can stay and we'll make sure you set up a private meeting with you with potential customer, supplier, or just partner or friend so you can follow up on behalf of the fantastic, amazing